continue our discussion with MRI. And I think last time we were talking about MRI, we introduced the concept from a physics point of view. And also we talked about some of the fundamentals of, or at least the fundamental physics that is related to the modality, the MRI modality, the magnetic resonance imaging. Can somebody quickly remind us where we were last time? Can just very quickly remind us where we were last time, and then I'll pull up the slide so that helps you to focus, or at least helps you to answer the question. Somebody? Okay, we'll start here. Okay, go ahead. No, just before that, let's just give us the idea of MRI. What's the idea behind magnetic resonance imaging, the physics behind it? Somebody, we're talking about something called magnetization, net magnetization, vector, things like that. Somebody? Somebody? Yeah?
When we open the MRI, it will align.
When you start the magnetic field, when you turn the magnetic field on, what happens to the... What aligns what? Yeah, but
hydrogen atom.
the
Proton.
yeah, proton. What's the proton look like? What did we model the proton as? Somebody remember it? It's What did we call it? We call it the magnetic moment, right? And what happened if you and precession. Okay, so it's randomly precessing. You can see it here. And then once you apply a magnetic field, what happens to all of these guys? Align or de-align. And the sum of these, what happens? Not all of them cancel. Some of them will give up. When you sum all of these as vectors, what happens? What happens? You get a net magnetization. Okay, a net magnetic moment that is not equal to, that's not equal to zero. So that means you will always have net magnetization. Okay, so that was the first thing in MRI. So this is magnetic resonance imaging. The first thing that we want to talk about is the concept of something called net magnetization. Net magnetization. And what we mean by net magnetization is that you have these protons which are readily available. There's a lot of them, and they're continuously precessing randomly. And we talked about the precession motion, right? Does anybody remember what precession motion looked like, or what is it?
Spinning around itself.
Okay, somebody else? Yeah. It's two types of motion in one, right?
Spinning around itself.
Yeah, it's spinning and doing, yeah, exactly. So, and when you apply a magnetic field, what happens? All of these guys, so what we end up with, if you think of it as, in terms of physics, you have a vector, right? And net magnetization, so which is basically the sum of all these magnetic moments, and it is continuously precessing. And I think we had a picture that showed us what precession means. Right? We had a very nice picture which shows us what precession means, and the frequency of the precession, we can calculate it very easily. Remember? We calculate it from this equation where F is simply equal to, the precession frequency is equal to what? Yeah, it depends on the magnetic field, which we'll call it today V0. Because later on today in the lecture, we'll see that there is another thing that we need to add. So what does this mean? Those of you who were awake the end of the last class, that means if I somehow, not somehow, but now I know, if I calculate the precession frequency, F, from the magnetic field, which I know, that's what you set in the machine, right? When you turn it on, you set that's the magnetic field. Then you can calculate the frequency. Remember, this is constant, right? It's a general magnetic relation, it's constant. For hydrogen, it's equal to, what is it equal to? Yeah, it's 42.53. Now, if I know that, then I know the precession frequency. And if you remember towards the last class, we were saying that if you know, once you know this, that if you apply a magnetic radio frequency, which is electromagnetic wave, if you apply it at the same frequency, then you get something called resonance. Thank you very much. So the first thing we want to start with today is the concept of resonance. Okay? So, let me just pull out this video just to show. It will show us what is the meaning, the meaning of the concept of resonance. Let's just.
We can introduce a magnetic field, and the compass needle will adjust itself along the direction of the field.
Just before it starts, now remember, I'm going to take this needle. Everybody knows the compass needle, right?
Yeah.
And what I'm going to do, or actually the video is going to show you that what happens when you apply a magnetic field. Okay, so you know what's going to happen. It's going to the north will align. We wanted to think of that. It's exactly the same way as when we turn our magnetic field on in MRI. So once I turn the magnetic field on, then this will align with the magnetic field that I applied. And then it will just toggle a little bit, and then eventually it will sit still. And after that, let's watch that first. So there we go. You apply a magnetic field, and then what happens?
Like a pendulum, it will oscillate before it comes to rest, pointing along the direction of the field.
Okay.
Here, one full oscillation of the needle takes approximately 2 seconds. The oscillation frequency is therefore around half a hertz. The relaxation time is seen to be around 10 seconds. Let's adjust the magnetic field down by a factor of 2.
Okay. So that you change the magnetic field.
I remove the needle and put it back in.
And you see again.
We can now see that the oscillation happens significantly slower. In fact, the vibration frequency is proportional to the magnetic field.
Okay.
Let's adjust the field back up. I remove the needle and put it back in.
Okay. So far,
once again, we see the vibration of the magnetic dipole. As long as the needle vibrates, it generates an oscillating magnetic field that we can detect with a coil. This is the MR signal that here disappears on a timescale of 10 seconds. Our task now is to make the signal reappear without touching the needle.
Okay, so now
for this we need a second magnetic field perpendicular to the strong B0 field.
Because this is where the second part of the MRI process is. Because the first part, you just apply the magnetic field, right? And when you apply the magnetic field, what happens, they all align, and you saw that. Now, we want to apply something else, which is the radio frequency. But remember, it has to be at the same frequency as the precession frequency. And therefore, when they are at the same frequency, then you get this huge oscillation, which means what? Which means that the needle gained energy. Right? The oscillations are going to get bigger, so that means it gained energy. Where did it gain energy from? That's what we wanted to see, from the resonance effect. So let's see that. Follow that, and then I'll come back to it afterwards. Okay, so
we call this weak field for B1. The B1 field pushes one end of the needle and pulls the other. Since B1 is weak compared to B0, it just rotates the magnetic needle slightly. If we remove the B1 field, the needle resumes its direction along the B0 field. This vibration is too weak to generate a measurable signal. We need to make the needle oscillate more.
Right?
This can be accomplished by repeatedly pushing the compass needle with the B1 field.
Okay.
We pursue this idea by making the B1 field oscillate. Our first attempt here does not seem successful.
Okay, now,
the needle does vibrate slightly, but not enough.
Now, did you see what he did? He just introduced the frequency. So that means he is adding another type of energy, but at some specific frequency. At the beginning, the needle was not affected. So he just picked up some frequency, and you see that the needle turned or oscillates a little bit, but was not affected greatly. But see what happens when he adjusts the frequency so that both frequencies are the same, then you see what's going to happen. When both frequencies are the same.
To give a measurable signal.
Oh, yeah.
We can improve the situation much if we adjust the frequency of the B1 field to the natural vibration frequency of the compass needle.
So he's adjusting the frequency. See now?
Repeated weak pushes can have a large effect when applied in synchrony with the natural oscillation. This is a resonance condition.
That's a resonance condition.
You use the same principle when you want to make a child in a swing move.
Yeah.
When applied to magnetic resonance, the B1 field pushes the compass needle in synchrony with its natural oscillation. Only when the resonance condition is met, the weak B1 field has a large effect.
Okay, so this is what resonance is. Okay, resonance, or the importance of resonance frequency. Once I define or I find what resonance frequency is, then I can set my RF to be at the same frequency. This way, the energy will be transferred to the protons, and they go from their let's say equilibrium state into an excited state. Okay, so they go from this, let's say the Z, we call this the Z, right? Which is the Z, we're taking the Z as the long axis of the patient. Right? Once you apply an RF, so apply an RF frequency, RF EM wave at some frequency which is the same as this guy, same as this frequency, then what's going to happen, this will gain energy and then will go to the excited state. Okay, so it will go, this is the ground state if you want. This is ground state. And once I apply the radio frequency, it will go to the excited state. It simply means that it has more energy. Okay? Now the question is, you say, okay, what the heck is it? So what? Now, what happens when I remove the frequency? What's going to happen? It will go back. It will relax. Right? Remember, if you, let's just say, put some numbers here. So this is excited state. Let's say E2. And this is E1. And now when it goes from E2 to E1, what is it going to do? That's it. It's going to give off energy. Okay? Because when it's going back, it's going to give off energy. Well, in that energy given off, it will be in the form of electromagnetic energy. If I somehow have a detector, right, that detects that energy, then I can look at it, analyze it, and use it as my signal, and that is my MRI signal. That's the signal we use to get the image. This signal here, when it relaxes or it gets excited, so what happens is that when I apply RF, and this you should write down, when you apply an RF signal, so the magnetization, right, which was along Z, we'll call it MZ, right, it will gain energy, and then we have some of these moments will be excited and will go to the excited state, which means that they have more energy. What's going to happen? Let me just go back to the PowerPoint. If you notice here that, okay, at the beginning I have a net magnetization, okay, that is along Z, and as I apply an RF signal, then I'm going to get more of the X. If I call this Z, and this is my XY plane, so then I will have an MXY, a magnetization that will develop in the XY plane, in the transverse plane or perpendicular to the initial one. Okay? It's a little bit, we need to say a little bit more about this. Okay, so yeah, let's look at this. This will show us, again, another, actually, okay. See if we get it done, because this will show you what happens when you apply the RF. And where am I? Okay, let's see here. Okay, so these guys are spinning. They're aligned with the magnetic field. Okay, so and then I'm going to, as you can see in a minute, I'm going to apply an RF signal. When I apply an RF signal, what happens is they get excited, right? They go from the Z direction, if this is my Z, and then go to the XY plane. Okay? So that means and then if I turn it off, what's going to happen? If I turn it, when I turn that off, then there you go. This went back to this one, and as it goes back, it gives off a signal. That's it. It gives off energy, and that energy, when I detect it, I can analyze it later on and use it for my MRI or the image. Okay, so that's, now let's just carry on because we were, yeah, this is a good picture that shows what goes on. Okay, so this is my patient, and that's my Z direction. Okay? And I first apply my magnetic field, let's call it this B0. So I first apply my B0, and then when I apply my B0, what happens to the net magnetization? What happens to the magnetic moments? Yeah, they will all align or de-align, and I get the net magnetization along the patient's long axis. And if I apply an RF signal, that's my RF signal that I'm going to apply, which frequency is the same as the precession frequency, right, at resonance. Then it's going to interact with these and excite the magnetization of the magnetic moments of the photons. And as a result, when they go back, I get that give off signal or give off energy, electromagnetic energy that is detected on the other side. And then once I detect that energy, I go to the second stage where the signal analysis procedure. Okay? Is that clear what goes on? Is that clear, the picture or what goes on? Because if you understood that, then we can go to the next stage where we see the most important parameters for us to get the MRI signal. Okay? So I don't know if we've seen this picture or not, but this is the patient depicted with all these protons or magnetic moments. They are randomly oriented. Okay? And then I apply a magnetic field, and then they are aligned or de-aligned. Okay? So the second thing that we wanted to look at, I think the best, once you apply an RF signal, then there are two things that you should notice here in these two pictures. In the top picture, you see that when you apply the RF signal, what happens to the Z magnetization? It decays. In physics, we say it decays, so it just shrinks, right? Why? Because some of these vectors will be excited. So they will be subtracted, right? So you go from a net magnetization along the Z, and then it starts to shrink or decay, right, until it goes to 0. Now, on the other hand, what happens to MXY? It grows, right? So you see here, again, this shrinks and this grows. So we have two things. We have a decay and a growth. We have a decay in MZ and a growth in MXY. And these are your two parameters that are in. The decay constant, right? And then the growth or the exponential growth constant again. So these are what usually referred to, I don't know if you've heard of these in your introduction course or not. These are called T1 and T2. Have you seen these before? No? They're called the T1. Yeah, you've seen them in MRI. If you're in your introduction course to MBI, you must have seen these two. The T1 relaxation time and T2 relaxation times. So in the next 20 minutes or so, we wanted to discuss what these T1, T2 relaxation times are. And remember, they are related to the growth of XY or the decay of MXY and the growth or decay in MZ. Yes? Yeah? As you apply the RF. Remember, initially, you have this guy, right? When you first apply, that's right. When you apply the magnetic field, right, you get this alignment and you get a vector, let's call it MZ. And then you apply your RF, and what happens when you apply your RF? Then some of the protons will get excited, and then this will shrink as a vector. Just think of it as a vector. This will shrink, and what happens to this one? Will grow. That's right. Okay? So let's see that. And I think it's better shown in this picture very well. Okay, so the T1, T2 are also called the longitudinal relaxation and the transverse relaxation. Just when you read that in the book, you see what that means. Okay? Okay, so you can follow the picture, or at least this, where initially you have all of these guys oriented the same, oriented in the up direction and in the excited direction of the ground state, and then adds up to 0. And then as they align, we see mz grows, right? And then it continues to go until you go back to the initial magnetization when you first turn the magnetic field on. So let's look at these two, and we've discussed this many times. We wanted to look at this mathematically. And by the way, this is the most important thing in MRI analysis in physics, is these two, as I said, the T1 relaxation, which is called the longitudinal relaxation, and T2, which is the transverse relaxation. So in T1, we're talking about MZ. Remember where we are. We apply the RF signal, right? So now my Z magnetization is all XY, right? It's zero. It's all XY. And then when the RF signal is off, then what's going to happen? Will grow, right? Will grow until it. So at the beginning, it will be zero, right? So remember, this is MZ. MZ is along the long axis. So MZ is the magnetization along the patient long axis. So this is this axis, right? So this will, once I turn the RF signal, it will be excited. If I turn it off, then it will relax or go. Yeah. So at the beginning, it's equal to zero. And then it will continue to grow until it reaches something called saturation, or the original value. Okay? Now, it's described by this equation. MZ is defined as M0, which is the initial magnetization when you first turn the magnetic field on, multiplied by 1 minus the exponential of minus T over T1. Okay, because it's an exponential growth. Now, what I want to use this equation for, and I'm sure you're going to see this somewhere in the quiz or the assignments or in the final, I want to use this equation to determine or define what T1 is, capital T1. What is this T1, what is it equal to? I want to use this equation to get a definition for that. Okay? Now, before I do that, let me, remember, I always say in physics, the first thing we do when we have an expression that describes a phenomena, the first thing we look at the limits, something called the limits. Okay, the limits means what? Means what's the extreme limit on, let's say, the two extreme ones. Now, what are the limits here? The limits are determined by t in this case, which is the time, duration, not t1. T1, remember, it's a constant, right? So let me see what happens at the beginning when t is equal to 0, because time starts from 0, goes to infinity. These are my limits, from 0 all the way to infinity. Now when t is equal to 0, e to the power of 0 is equal to 1, right? And 1 minus 1 is 0. So at the beginning, the magnetization is equal to what? 0, which is true, right? So at the beginning, the magnetization is equal to 0. Now, so this mz is equal to 0. What happens when t goes to infinity? When t goes to infinity, I have something over infinity which is equal to 1 over infinity is equal to 0. 1 over, because this is e to the power of minus infinity, which is simply 1 over something to infinity. 1 over infinity is 0. Right? Okay? So that means this guy is 0. And then, so this gives me mz is equal to m0. And that's what we have. If you go all the way to somewhere infinity, then you go back to m0. Okay? So these are the two extreme cases, 0 and infinity. Now, what I want to do, what happens when t is equal to t1? So I just come in here. I say, okay, set t equals to t1. That means I have 1, right, minus e to the power of minus 1. If you have your calculator, just take 1 over e. See what that is equal to. So that's what 1 e to the power of minus 1. You see somebody tell us what's e?
0.36.
Say again? 0.3. Okay, so this is equal to 0.3. So that means, let me go to this side here. So that means when T is equal to T half, then I have MZ is equal to M0 multiplied by, what did you say? 1 minus, what's 1 over E?
1 over E?
Yeah, 1 over E. 0.37, right? Right? Something like that? Okay. What's 1 minus that? 663. So 0.63 M0. Can somebody use this, what we've done, to define T1 for us? Somebody? Yeah, use what we've done here. It's mathematics. What I've done is just simple mathematics. I just took T at the time to be equal to this number that we call the decay constant, well, in this case, the growth constant, and we equaled that to it, and we wanted to see what this time is equal to.
So what do we put 0.37?
Because it's 1 over E. 1 over E, right? Because this is, when this is equal to T1, let's look up here. When T is equal to T1, T1 over T1 is E to the minus 1. E to the minus 1 is simply 1 over E. I just wanted to simplify it for you to calculate it in your calculator. When you calculated that, it turned out to be 0.37, and when we subtracted from 1, we get 0.63 M0. Can somebody use this equation to tell me, or to tell us, what the definition of T1 is? What's the definition? What's the significance of T1? What does T1 tell us? It's a time, right? So it must be, it's the time taken the signal to, not the saturation, no? That's right. See, you got it. So if you look here, when T time is equal to T half, the signal, or MZ, grows into 63% of its initial value. Did you get that? So the definition of T1, the relaxation time T1, is, can somebody give us a definition of it? Somebody. The definition of T1, capital T1. It's the time taken the longitudinal signal to reach 63% of its initial value. Okay, you get that? Well, I want somebody else to repeat it. Okay, now I said it, I want somebody to repeat this.
It's the time to release it.
It's time needed
to take the
longitudinal
to reach the 0.63%.
63%. Guys, remember, 0.63 is 63%. Right? 63% of its initial value. Okay? So T1 is the time taken the signal, or in this case the magnetization, to reach 63% of its initial value. What does that mean? That means in my signal processing procedure, as soon as the signal reaches 63%, I take a reading. That's if you want to relate it to the application. This is how you take the signal, or you take the reading, that's it. Okay? So T1, again, because I'm sure you're going to be asked, and I'm sure you're going to be seeing this T1 throughout your MDI career. T1, T2. So T1 is, what's the definition again of T1? Yeah?
It's the time needed for the magnetization.
Longitudinal magnetization?
Yeah, to reach the signal of 63%
of the initial. Thank you very much. Excellent. Somebody from this side again? Somebody? Guys, come on. What's T1? I'll pick it. T1. Yeah, go ahead.
The time taken along the tunnel to reach the signal 63% of the emission.
Excellent. Initial value. All right. So this is T1. So the excited protons then returns progressively to their lower energy state. Remember, I've always said that the excited state is, after they absorb the energy or they gain the energy from the RF, they go to the excited state. And if you turn that off, what happens? Yeah, that's it. So this excited state or relaxed state or ground state. Okay, let's. These are, by the way, whatever I wrote there is summarized here. Okay, when t goes to infinity, when t goes to 0, and when t goes to t hat, which is 63%. Just you need, you need to write t1 here. I forgot to write that. Okay, so if you miss my writing or you can't read that, then it's summarized for you over there. Okay, let's look, which I explained. Now we wanted to look at the decay of, because what happens here, if you look at just x, m, x, y, what happens? At the beginning, it's maximum, right? And then as all the protons go back to equilibrium, then it shrinks. It decays. Okay? And you can follow that until it goes to 0. Okay, so let's look at that mathematically. So if you look at mathematically what happens, so this is the T2 relaxation time, which is the transverse. Transverse means Arabi, if you're interested. So in the perpendicular to the plane. So it was at the beginning, it was this, it was in this plane, and then it relaxes or it decays as these guys relax, it decays to go back to 0. So initially it was at the maximum value, m0, and then it decays according to this equation, decay equation, which we're very familiar with. So now this is T2. This is T2. So the transverse, which is along the xy plane, this is my xy plane, right? The transverse magnetization will decay in accordance to this equation, m0 exponential minus t divided by t2. And this is my t2 relaxation time. Okay? Again, we wanted to do the same thing. We wanted to look at the limits, and then we want to use the equation to find the definition of t2. Right? Guys, remember, this is probably your only course that is going to discuss the mathematical definition or define these T1, T2 for you from a mathematical, using a mathematical approach. This is a physics course, I have to remind you. Okay, so when t is equal to 0, what happens? Yeah, this is 1, right? And then mxy is equal to m0. And that's exactly what we have. At the beginning, when t is equal to 0, the magnetization is maximum at the initial value, which is the initial value. And then, as time goes by, when it goes to infinity, right, as t goes to infinity, mxy, what is it going to be equal to? m0 e to the power of minus infinity. 1 over infinity is equal to 0. So that means this is equal to 0. And that's exactly what you have. If you wait for an infinite time, all the way, then the magnetization, the transverse magnetization goes to 0. Again, same question. We wanted to see what happens when t is equal to t2. Well, let's set it up here. If that's the case, then mxy is equal to m0 e minus 1. Okay, so 1 over e, which is m0 over e. What's e? We already calculated that, is 37. Okay? So this is equal to 0.37 m0. Can you use the same argument to tell me what T2 is? Same argument as we had before, and you just to tell me what T2, the definition of T2. You want to try?
The time needed for the transverse magnetization to reach 37%
That's it. You guys hear that? Yeah? Somebody from this side?
The time is taken to reach transversal.
Yeah, magnetization.
To reach the 37%
Of?
of the initial value.
That's it. So this is the definition of T2. Okay? So T2 is progressively lost. So there is a loss in this magnetization, the transverse magnetization, being characterized by this form. It's called relaxation, where the transverse magnetization decreases to 0. When does it go to 0?
When it's reached
Infinity, right? When time goes to infinity. All right. So I think we've done, or at least we've finished part 2 of the procedure, the magnetization, or the, sorry, MRI procedure. Because the first part, we applied the magnetic field, right? We know what that does for you. And the second part, we applied, what did we apply after we, the RF signal, right? The radio frequency, which is an electromagnetic signal, right? We applied the RF signal, and then we saw what that gave us. Now, so this is, we've done a lot of what we need to do in MRI. So the first part, so this is MRI procedure. First part, we simply apply B0, and I said I'm going to come back to why I'm going to call it B0 in a few minutes. But the first thing that I apply B0, and then I know what's going to happen. What's going to happen? I am going to get net magnetization, right? And then step number 2, I'm going to apply an RF signal. RF signal. Can somebody summarize this for me, what the conditions are here and what is the consequence of applying this? What sort of frequency, and just a summary of what we've just... Yeah. I need somebody else. Can someone, Khalid, do you want to try? What happens when you apply an RF signal?
That will align, the net force will go to...
Not net force, net magnetization.
Magnetization will go to the excitation.
Okay, somebody else? Give this side. You guys are a little bit sleepy today. Okay, what happens?
When you apply the RF signal,
Yeah.
it starts moving, going to the excitation state.
Okay.
Then when you move the RF signal, it returns back.
Okay, now one thing that you missed, which I started the class with resonance. What's the idea behind the resonance frequency? What's the significance of the resonance frequency? Because remember, MRI, magnetic resonance, there is a big part of magnetic. Yeah, what's the resonance? Resonance occurs. That's it, the same as the precession frequency, which we know. How do we calculate the precession frequency? A formula I started at the very beginning. F is equal to gamma multiplied by B0, the magnetic field. And gamma is constant. Okay, remember gamma, the geomagnetic ratio is constant. Okay? So anyway, so once we apply the RF signal, we are sorting business, except we're not there yet. This is two major parts. The third part that I'm going to try to finish, hopefully today, which is applying gradient field. So gradient field. Let me just explain what that means first, and then we'll go into what we need to do. Now, let me ask you this question. Now, when you apply this signal, okay, so you apply the RF, and you have your patient lying down, okay, and I think I have a slide with the patient. This is the, okay, all right? So you applied your magnetic field, and I'm going to use vectors to represent the magnetic field. And this is your patient inside the magnetic field. Is there any way, or do you think there is any difference between the exposure of any of these protons into the magnetic field? If I wanted to look at, for example, calculate the frequency at any point here, if I want to calculate the resonance frequency here, right? What's the resonance frequency? F is equal to B times gamma. So it will be the same here, the same here, the same here, the same here, the same here. Meaning what? Meaning that I will not be able to distinguish between the different parts that I'm looking at. Okay, I will not be able to say, okay, I'm looking at this region or that region or that region. Why? Because they all have the same frequency. Hydrogen is hydrogen, right? And the magnetic field is the same. So the question is, how can I eliminate that? How can I introduce something, some fancy technique by which I can distinguish between the what region am I looking at? Can somebody think how? Yeah, Nafis?
Maybe by the amount of hydrogen in that region. Concentration.
Not there. Not there yet.
We use little amount of.
We need something we control. Engineering, something is related to the design of the equipment. I design it in such a way.
To limit the frequencies coming out from the machine.
Well, you should just look at
Just
this.
have it the same concentration all over.
What happens if I can, through some magic engineering approach, I can introduce something so that the magnetic field is different across here? If I do that, then I'll be able to successfully look at specific regions. Now, my problem here is that the field is the same, right?
Yeah.
Right? So I can't distinguish whether I'm looking here or looking here or looking here. But if I somehow change the magnetic field so that the magnetic field is different everywhere, then if I select the frequency, it will look at that only specific region. Yes?
Is it like putting a plate or a device on the...
It's called a magnetic gradient. That's what the gradient field. That's right. We'll see it in a minute. So the idea is to introduce, you know what the word gradient means?
No.
Gradient is that when you have to add or subtract a small amount from the field. Okay, so instead of the field here, if it's static or uniform, so the field here is 1.2 Tesla, then I introduce a gradient field, that means the field will not be uniform. So the effect of the gradient field is so that, we'll come back to this in a minute, so that the field, magnetic field, when I say the field, I mean magnetic field. The field is not uniform across Z. You know what Z is, right? Z is what? The long axis. Yeah, the long axis of the patient. Okay, let's see if I have a diagram for that. Now, this is my B0. Okay? This is the value which is constant. This is the B0 that I first turned on. And then, if I somehow, just so like I said, I have some solenoids or gradient fields that I can introduce big gradient here, smaller gradient here, smaller gradient here, smaller gradient here, and on the other side I can do it so that I can select where to look. This will help you where, let's say, because the total magnetic field will be BZ, which is my, it will be B0 plus some value which is these vectors. So that means instead of having uniform field, what am I going to get? I'm going to get a variable field, a field that is not constant throughout. So that means instead of having something uniform like this, I'm going to have something variable like this. And if you can see, this is my patient here. So if I set my RF here, that means I'm going to look at this region only. Right? Because anywhere else, it will not be at resonance. You guys get this? Outside of this region, the protons will not be resonating. They will not be excited. So this way, I will only look at this region only. Let's look at an example. So what I have here, I have my patient, okay? And it's in a magnetic field, some constant magnetic field, which in a minute, let's say some value. And then I'm going to introduce a gradient field. So what happens is that if I have B0 is equal to 1.2, in this region here, it will be 1.2 minus 0.25. In this region here will be 1.2 minus 0.2. So specifically in this part here, in this part here. So if I am interested in imaging this side, then my B total will be equal to 1.2 minus 0.2, that is equal to 1 Tesla. So if I wanted to image this region here, what should my frequency be? What should my RF frequency be? Come on. F is equal to what? Gamma, which is constant, multiplied by 1. Right? Because that's what my magnetic field is. 1.2 minus 1. So that means all of these guys are not at resonance. The only one that is at resonance is this region. Okay? Got it? Just wait. Give me 1 second and then I'll give you one to ask question. Now, what happens if I wanted to measure or look at this region here? What do I do? If I wanted to look at only this region here, right here, suppose that, so my B total would be equal to what? 1.2 plus, let's say here, 0.1. So that means my magnetic field will be equal to 1.3. So that means my frequency is equal to what? Gamma multiplied by 1.3. Got it? This is the significance of what? We have two questions, right? Let's look at the, somebody has a question? Yeah?
You said that they're not resonating, right?
The only, yeah.
But they are all aligned, right?
Yeah, they're all aligned, but they're not excited. They're not resonating. That's a very, very good question. Yeah.
It's not a question, just can you repeat the second part?
The second part, this part here?
Yes.
Okay, so suppose that, I'll ask you the question so that I guide you through it. So suppose that we wanted to image this side, this region here. Now, definitely this is going to be much narrower, right? But just for this argument's sake, suppose that I want to look at only this region. And I want to make sure that I'm not looking at anywhere else. So what do? My magnetic field here is equal to 1.2, which is my static field. That's why I called it, by the way, that's why earlier I called it B0, right? So 1.2, and then I add to it this gradient. That's my gradient field, by the way. This is gradient field, and so is this one. So it's this one, gradient field. Okay, so the gradient field means what? It varies. It varies as you go across the patient. So when I'm here, my total magnetic field is equal to 1.2 plus 0.1. That means 1.3. When I want to select my resonance frequency will be this gamma multiplied by 1.3. I think 1.3. I think that's the one you're referring to. So this is 1.3. While here, my magnetic field is equal to 1.2 multiplied by minus 0.2, it's equal to 1. So my frequency here is equal to gamma multiplied by 1. That's for this region here. And for this region is 1.3. Okay? You guys see the significance? Okay, can you tell us? Yeah? The significance of the gradient field. Because remember, guys, these are three very important parts of a magnetic resonance. The B0, okay, that's the first thing you do, and then the RF, and then the third and the third important part is applying the gradient field, or the addition of a gradient field. Can somebody tell us what's the significance of the gradient field in MRI? Okay, go ahead, louder. So to select, okay, and how do we do that? Let her finish. By adding the gradient field. So instead of looking at the whole z-axis as one magnetic field, uniform magnetic field, every part of the z, by the way, they call it spatial gradient field. Do you know the word spatial? What is the word spatial? Position. Spatial, not special. No, spatial, from space. Spatial, yeah. So spatial, that means with position. So this is a spatial gradient field. That means every position as you go across, it's different. So if you select some specific region, some specific point that you wanted to image at, so what is the magnetic field here? And by the way, the gradient field is known to you. So if you, as an operator, say, no, I wanted to select that region, so you just go to your computer and you select along Z, because that Z is known, right? Along Z, so for example, let's start from 0 at the bottom, right? And then I want 75 Z. So 0.75, that means here. In your computer, you know what that field is. You know what that gradient field is. You add it to your zero field, and then you set the frequency. And then you're in business, right? So you guys, is that clear? These are very important points or important components of the MRI system. Okay, the first one is the B0. Okay, the second part is applying the RF signal, which this gives me the T1, T2. So this will give me T1 and T2 times, the relaxation times, and then applying the gradient field, which gives me the non-uniformity. So the field is not uniform anymore. Any questions? Just let's make sure that we understand these. Yeah, go ahead.
Is the gradient field
Fixed?
like this reason?
It varies with Z. It's not fixed. It varies with Z. I know at some point, yes. If you, let's say, pick some point along the Z axis, that value is fixed. But it varies along Z. You want it to be varied along Z. If it does not vary, then it's not going to give you what you want. It's not going to produce your unit. Somebody here. Yeah. Yeah.
How do I know it's adding or subtracting? Is this fixed?
It's very easy. Engineering-wise, very easy because a magnetic field is a vector. So it depends where it's pointing. Usually magnetic fields will go like this, right? So if out of the page is positive, into the page is negative. But this is the vector. You know, vectors have magnitude and direction. So that's taken care of. The add or subtract, that's very easy. Okay. And by the way, as I said many times, you know exactly where it is as a function of Z. And Z is the long axis. Okay? Any questions before we start? Okay? No more questions. So now, at least just before we close at least our discussion of the gradient fields and the radio frequency signal and the applied magnetic field. Now, the second thing we wanted to talk about, once we've done everything, now we have left, I think, 2 topics left for us. There are some safety issues that we discuss, because safety-related issues with MRI. And we know some of them, let me just ask this question. In terms of safety, what is the main thing that you have to be concerned about in MRI? Shielding? Metallic, yeah, because you're dealing with magnetism. So the main thing that you have to worry about is that this magnet that is huge, and you want to make sure that, for example, your patients do not have any implants, tooth fillings, metallic tooth fillings, or some braces, or some, things like that. So, but in terms of ionization, do we have any? No, why not? That's right, because we're dealing with something in the RF range, which is very, very low frequency, and that's way below the ionizing range of electromagnetic waves.
So it's safety.
Huh?
Safety.
Safe.
Yeah, of course. Yeah, of course. It is. The only thing about it is that it's too expensive, right? Okay? So we have, I think, about maybe half an hour more to do on this, and of course the remainder of the class next time will be on, we have a group exercise on MRI, just to make sure that, I think you are most happy with this group work idea. So we'll continue doing that so that you'll learn. And of course we have the midterm. Yeah, the midterm next class.
Can you remind us what's
The midterm? Okay. It will be mainly, where did we leave last time?
from last lecture?
Yeah, midterm 1. In midterm 1 we left, I think the last time we did radiation safety, right? Radiation safety? Let's just, I actually, I'll have to go back to my notes and see how far did we cover. But from, let's just say from,
Radiation safety.
yeah, from radiation safety. Radiation safety.
X-ray interaction.
And then I'll tell you how far you go in terms of the, I just wanted to look up my notes and then we'll
And Doctor, what time is it going to be? Same time?
we'll have next time, be careful, you guys had to leave last time. We have 2 classes in a row next time, on Thursday. First class, okay?
We don't have class. We can we start from the beginning, like from 9:30 because we have another
That's
class.
fine. Can we start from 9:30?
Yeah.
Okay, we'll start from 9:30. And then we'll go till the first class will take just our regular class, and the second class will take the midterm. Okay, any more questions? Yeah.
What about the ultrasound?
We will have at least 1 session on it, just to make sure that I give you the basics of it. Inshallah. Yeah. Can't hear it, huh? remember we said at the very beginning, we'll see how the second midterm is, and then we'll see the weights. 30, I think, 30. Yeah, well, there's a makeup. Right.
you will take the best.
Yeah. Okay, so 30 is for the midterm, and then we'll see the project. The most important thing is the project. Yeah. Make sure you guys hand in the project on time. Make sure you follow all the instructions. This one is on the